Okay, so we continue to discuss section 7.8. All right, so we have shown the covariance matrix lambda of n random variables x1 up to xn, x non-negative definite, and the eigenvalues of lambda are all non-negative. Okay, and now we consider the case that lambda is singular, and we let R be the multiplicity of eigenvalue 0 of lambda. Okay? And since lambda is singular, so the multiplicity of the eigenvalue 0 is clear that R is in between 1 and n. So the rank of lambda, okay, is k, which is equal to n minus r. Okay. Now we let v1, v2, up to vr be orthogonal eigenvectors. Okay. Oh, also normal. So we want the length of each v sub I to be 1. Right. So the also normal eigenvector, all right, eigenvectors of lambda corresponding to eigenvalue 0. Okay. So then we have that. Okay, lambda vi is equal to the 0 vector for all I from 1 to r. And then the quadratic form okay, so the quadratic forms of vi transpose lambda and vi, okay, should be equal to 0, okay, for all I from 1 to r. Okay, so which implies that the transpose of vi times the random vector, okay, x minus mu is equal to 0 with probability 1. Okay, for all I from 1 to r. Okay. So you can see that each bit of I give a non-trivial linear relation, okay, among random variables x1 minus mu1, x2 minus mu2, and x3 minus. We know that this random vector x okay. And the V I G of means that VI1 x1 minus mu1 plus VI2 x2 minus plus plus VIN is equal to 2 with probability 1. Okay, so that this goes to here. Oh, yeah, I just right here. Okay, all right, and so we write. So this R linear relation can be rewritten in the following form. Okay, so we can have V1 transpose, V2 transpose up to VR transpose. Okay, x minus mu, which is equal to 0, 0, 0, with probability 1. Okay. Now we let W to be this matrix V1, 2, V2 transpose up to VR transpose. Okay. Which is an R times N real matrix of rank R, because that the R rows are orthogonal, so they are linearly independent. Okay, so the rank of the matrix R. Okay. And without loss of generality, okay, we assume that the last R columns of W, okay, form linearly independent set of vectors in R. Okay, as we know, matrix W has n columns, and because the rank is R, so we can always find R columns out of the n columns, which form a linearly independent set. Okay, and so without loss of generality, we just assume that the last R columns of W form a linearly independent set. Okay. Otherwise, we just permute, okay, the n columns of W, and of course we do the same. So do the same permutation on the random vector X, or on the random variables xi's, okay, in the xi minus mu i's in the random vector x minus mu, because this random vector has n components, so we do the same permutation on the components of this random vector. Okay? Right? So now we can partition. So we can partition W as W equal to minus W1, W2. Okay, and this matrix R times N, all right? And this matrix would be R times R. So the second matrix W2 consists of the last R columns, and this matrix is R times N minus R. Yeah. Okay. Right. Now we let the X vector, okay, and we partition. So the size here, this is R, this is N minus R, and the mu mu2, the size N minus R, this size R. Okay. All right, and so now we have, okay, so this one, this is W, right? So W times X minus mu is equal to 0 vector with probability 1, right? And so now W is minus 1, minus 2, and here is x1 minus mu1, x2 minus mu2. Okay. Right, and the 0, okay, with also 0, 0. Okay, this is N minus R, this R here. Okay, so so we have oh, by the way, sorry, 0 is probability 1. Sorry, we don't need to decompose them. Okay, and so so we see that we now have minus W1 times x1 minus mu1 plus W2 x2 minus mu2 here. Okay. Okay, and so let's check the dimension. This one is r times n minus r. Okay, and this is n minus r times 1. This one is r times r, and this is r times 1. Okay, and so this is, and this is r times 1. Okay, with probability 1. And we move this to here. So we have move this term to the right-hand side. So we have W2 times x2 minus mu2 is equal to W1 x1 minus mu1. Okay. Now, because that the W2 is formed by the last R columns, and we assume the last R columns form a linearly independent set. So we know that. This matrix invertible. So it's an invertible R times R matrix. Okay? So this is okay. And so we can see that with probability 1. Okay. And so finally, we can see that x2 minus mu2 is equal to W2 inverse W1 x1 minus mu1. Okay. All right, so in particular, you can see that the x2 is equal to W2 inverse W1 and x1 plus mu2 minus W2 minus W1 mu1. Okay. With probability 1. Okay. So if we write it explicitly, which means that x r m minus r plus 1 up to x m minus r plus 2 up to xn. Okay. So here we have r random variables, and these random variables of the right. So it's actually each of the xm minus r plus I. It's a linear combination of the first m minus r random variables plus a constant here. Okay, plus constant. So this is right. So you can see this is a constant vector. Okay. With for V1. For V1. All right. So which shows that x2 okay, is an affine transform of x1. With per v1. So this is a surprising result, right? Because with here, we consider that the covariance matrix of n random variable such that it's non-singular, and the multiplicity of the eigenvalue 0 of lambda is r, okay? And then we can find random variable out of the n random variables, specifically without loss of generality, that we can find here the last random variable is an affine transform of the first n minus r random variables with probability 1. Okay, which means that each of the last random variables is a linear combination of the first n minus r random variable plus a constant. Okay, plus a constant. Now, since we look at x minus mu, x1 minus mu1, x2 minus mu2, right? And if we do the substitution, okay? So x2 minus, all right. So x2 minus u2, mu2 is this one, okay? So we can see this is x1 minus mu1, and here is w2 inverse w1, and x1 minus mu1. Okay, so that we have identity n minus r times n minus r, and this is w2 inverse w1, and this matrix has dimension r times n minus r. Okay, and here x1 minus mu1 with probability 1. Okay. All right, so we can have that. The covariance matrix becomes, right? So we can compute lambda, as we know is the expectation of the random vector multiplied with its transpose, okay? And we can substitute into here, okay? So we can move to there. So this is actually expectation of identity mu1, okay? And the transpose, so we have x1 minus mu1 transpose, and the transpose of this matrix. So the transpose of this matrix transpose, okay? And here, okay? And bilinearity of expectation. So now we have identity n minus r times n minus r, and this is w2 inverse w1, and the expectation of x1 minus mu1, x1 minus mu1 transpose, and the transpose of this matrix. This matrix. But this is the covariance matrix of, so this one, we say this is covariance matrix of x1. Okay, x1. x1 consists of the first n-1 random variables. Okay. Okay, and so now we have, so from that, okay. Now, so this is a matrix. So we see, so this is a matrix, all right, of rank n minus r, right? This is a matrix of rank n minus r. And we look at here, this is also a matrix of rank n minus r. So of rank n minus r here. And again, this is of rank n minus r. Okay. So which shows that this matrix, right? So this matrix is so this one is it is an R times R matrix. Okay, this is n minus r times n minus psi. This is an n minus r times n minus r matrix. Okay, all right. So that this matrix must of, so that this is of rank n minus r2. Okay, so this matrix must has 4 rank. Because if the rank of this covariance matrix is less than n minus r, all right, then the rank of this product, okay, the rank of this product will less than n minus r, which is a contradiction. Okay, so that. Okay, so that's lambda x1 is an n minus r times n minus r real symmetric matrix of rank n minus r, right? And then x non-singular, which means that this matrix is invertible. It's non-singular. Okay. All right. So we summarize the previous discussion into the first proposition in this section. Now, so the covariance matrix lambda of n random variables x1, x2 up to xn, xn n times n real symmetric. Oh, okay, it's a real non-negative definite matrix. Okay, so it's not only symmetric, it's also non-negative definite. Okay, as we defined for real case, any non-negative definite matrix must be symmetric. Okay. Right. Now, it is positive. It is non-singular. if only if it is positive definite. Of course, right? Because it is non-negative definite, so the covariance matrix has eigenvalue greater than or equal to 0. Okay, and if it's non-single, it means that there is no 0 eigenvalues. So all the eigenvalues must be positive. So in this way, the covariance matrix will be positive definite. Conversely, if the covariance matrix is positive definite, then all eigenvalues should be positive, and so that lambda has no eigenvalue 0, and so it is non-singular. Okay. And if it is singular, all right. So if it's singular and of rank k, so 0 k is in between 0 and minus 1. Okay. Then, so the rank must be less than n. Yeah, because if the rank is n, then the covariance matrix must be non-singular. All right, so the k should be. Then R equal to n minus k. All right, out of n random variables x sub I are an affine, okay, transform of the rest k random variables with probability 1. And this k random variable has covariance matrix, all right, whose covariance matrix is non-singular. Okay, this covariance is non-singular. Okay, so that this k random variable, because the rest k random variable has non-singular covariance matrices, so that this k random variable has positive definite covariance matrix, so that this n random variables, okay, they when subtract their means, they are not linearly dependent, so they should be linearly independent. Okay. Okay, so so you see from proposition 7.8.a, the covariance matrix of n random variables give us some information about the linear dependence among these n random variables. And specifically, this information can be obtained from the rank of the covariance matrix lambda. Okay. Okay, and so now we proceed to the subsection 7.8.2 about jointly normal random variables. Right, so we will define what are jointly normal random variables. Now we let Z1, Z2, up to Zn be n independent, okay, standard normal random variables. Okay, so that each of z sub I has zero mean and unit variance. Okay. And of course, because they are independent, so these n random variables are jointly absolute continuous with a PDF, which is the product of the PDFs of these n random variables. Now we let x1, x2 up to xm. All right, so bm random variables such that this n random variable is obtained by affine transform of the statistically independent standard random variables. So x1 is a11, z1 plus a12, z2 plus a1n, zn plus mu1, x2 is equal to a21, z1 plus a22, z2 plus plus a2n, zn plus mu2, up to xm. X sub m is a m1, z1 plus a m2, z2 plus plus a mn, zn plus mu m. Right? Okay, and then x1, x2 up to xm are said to be jointly normal. Okay. Or to have a multivariate normal distribution. Okay, so they have. All right, and all right. So when we can write this relation by in matrix form, right? M and mu 1, mu 2 to mu m, and the coefficient matrix A11, A12 up to A1n, A22, A21, A22 up to A2n, up to AM1, AM2 up to AMN. Okay, define this. All right, so this is M times M matrix. This is M times 1 random vector, and this is M times 1 random vector, and this is M times 1 constant vector. So the linear relation here, so this corresponding to that the x random vector is the coefficient matrix A times the z vector plus mu. Okay. All right. So we have this relationship. Okay, this relationship here. Okay, now, all right. So now, because Z1, Z2 up to Zn, they are independent, standard normal random variables. Okay, so look at here. So this is a function of z1. So this is also so the scaling of the z1, this random variable, is independent of this random variable, or independent of this one. Okay, and we know if we multiply with a constant, then then a normal random variable is also normal. Okay, so this is a normal random variable. This is a normal random variable. This is also normal random variables. And so we have independent random variables. When we sum together, okay, it also, again, normal random variables. And with mean, which is the sum of the mean of each terms. But as we know, the mean of this random variable is 0. Okay, so again, the mean of this sum is 0. The variance of this, okay, is because Z1 has univariance, so the variance of A11 Z1 is the square of A11. The variance of this term is the square of A12. And the variance of this term is the square of A11. So the variance of this sum is the sum of the square of all these coefficients together. Okay? All right, so this is a normal random variable with zero mean and the variance, which is the sum of the square of the coefficients. So when we add a constant, then this one, which means x1, is again a normal random variable with variance, with mean, which is mu1, and the variance is the sum of the square of the coefficient as 1i. Okay, so we now summarize the discussion. Okay, so we summarize the discussion that since Z1, Z2, Zn are independent standard normal random variables, AI1, Z1, AI2, Z2, up to AIN, Zn are independent normal random variables with zero mean and variance AI1 square, AI2 square up to AIN square, respectively. Okay. All right. So by proposition 6.3.2, okay, the sum. So AI1 Z1 plus AI2 Z2 plus plus AIN Zn is a normal random variable with zero mean and variance, which is the sum of the square of Aij. j from 1 to n. Okay? So that xi, which is ai1, z1 plus ai2, z2 plus ain, zn plus a constant mu I, right? It's a normal random variable with mean mu I and variance. Okay, and the variance summation of j from 1 to n aij square, right? For all I from 1 to m. Okay, so each except I, is normally disputed. Okay, not disputed. But x of i's may not be independent to each other. Okay. All right. So now now the mean vector of z, or the random vector v, z x is a 0 vector, okay? And the mean vector of random vector x, okay, as we denote here, we collect x of i's together to form the random vector capital X. So x mu x, which is just mu, okay, as we defined here, which is just mu here. So this is the mean vectors, all right? And the covariance matrix, lambda z, which is defined to be z and z transpose. All right, because random vector z has 0 mean. Okay, so we just of z, okay, is the n times n identity matrix. Okay, n times n. Okay, since covariance of z I zj is the delta of ij. Okay, when I not equal to j, zi and zj are independent, so that the covariance, okay, is equal to the product of the expectation of zi and the expectation of zj. But we know that their expectation are 0, so it becomes 0. And if I equal to j, the covariance of zi is become to the variance of zi, which is on 1. Okay. All right. So we see that the covariance matrix of z is the identity matrix. But how about the covariance matrix of x? Lambda x of xx. So we will compute it. All right, so that lambda x, okay, is the expectation of x minus mu x, okay, x minus mu x transpose. Okay, and this is x minus mu, because the mean vector of random vector x is mu. Transpose. Okay. All right. So look at here. X minus mu is A times Z. Okay. So you have A times Z, A times Z transpose. So this is A, expectation of Z, Z transpose, and A transpose, bilinearity of the expectation. And this is A, identity, and A transpose. So this is A transpose. Together, this is an M times M matrix. Okay. Okay, so the coherence matrix of random vector capital X is the product of A and its transpose. Okay, this is transpose. Now, and now, since Z1, Z2 up to Zn are independent standard normal random variables, they are jointly absolutely continuous with a joint PDF. Okay, so joint PDF f z about z. Okay, which okay, so joint PDF 1. Which is the product okay of the PDFs of each random variables. Okay, and so we have pi exponential j square divided by 2. Okay. Here. And so this is 1 over square root of 2 pi nth power, and exponential minus 1/2 summation j from 1 to n, and zj. Okay. Okay, and if we write in the vector form, we can write. So we can write it in this way: fz with z, right, is equal to 1 over square root of 2 pi nth power, and the exponential function 1/2. And what is that? This is the z vector transport with z. Okay, so this is the inner product. Okay, because that. So this one summation so this is z transpose z. Okay. Okay. So in terms of vector form, we have this succinct expression. All right. So this is the. So we know the z random variables. Okay, give us the joint PDF of these n random variables. How about the distribution of, as we know, that each x sub I, we know each x sub I is a normal random variable. What is the joint distribution of x1 up to xm? Right. So what is the joint distribution? Okay. Now we consider a special case. And stated in the following proposition. Okay. If m equal to n and A it's an n times n non-singular matrix. Okay, so the case is that we have the same m equal to n. Okay, so m is equal to n. So they have the same number of xi's with the number of z's, these j's. And also the matrix A is non-singular. Okay, matrix A is non-singular. In this case, then the n random variables x sub I the n, you say, the n jointly normal random variables x1, x2 up to xn, okay, are jointly absolutely continuous, okay, with a joint PDF, okay, and the joint PDF, okay, can return us the square root of 2 pi nth power and the determinant of lambda. Okay, lambda is the covariance matrix of x sub i's, and times the exponential function of 1 minus 1/2 and x minus mu transpose num inverse and s minus mu. Okay, where lambda is A transpose is the covariance matrix of xi's, and mu is the mean vector of xi's. Okay. So so in this spare case that m equal to n, okay, and A is an n times m non-singular matrix, right? And in this case, the n are jointly normal random variables, okay, are jointly absolute continuous, okay. Well, and the proof is quite simple. So we note that okay, a vector function, okay, an affine. Okay, so we look at the vector function g. Okay, so this is a affine function, and this function is a coordinate transformation from Rn onto Rn. Okay, this is a coordinate transformation. Why? Because that A is invertible. Okay, all right. So A is invertible. So it will transform a vector in Rn to a vector in Rn. Okay. And it's 1-to-1 and onto. Okay, so this is a coordinate transformation, and by theorem 6.7.b, okay, right? The n jointly normal random variables x1, x2 up to xn, okay, are jointly absolutely continuous, okay, with a joint PDF, okay. So with a joint PDF, right, which is just the joint PDF of random vector z divided by the absolute value of the Jacobian of the coordinate transformation, okay, of G. Take the absolute value, okay? And so we know now that what is the joint PDF of Z? Well, we have already computed it here. So this is the 1, okay? And square root 2 pi n, and exponential minus 1/2 z transpose z, okay? Times, all right? And so 1 over the Jacobian, but the Jacobian is just the determinant of the this function, all right? because it's an affine transformation, so that the Jacobian of G, we know it's a constant. So the Jacobian determinant will be determinant of A here. But the determinant of A, we know it's positive Y. Oh, sorry. Okay. Okay, yep. So the just determinant of A. Sorry about that. Okay, and so this here is the determinant of A. Okay, so here is the determinant of A here. Great. Now, if we move to join this together, all right, so we have 2 pi, and we have to take the determinant, the square of the determinant. Okay, the square of the determinant here. All right, and the exponential function here, minus z transpose of z here. Okay. All right. Now, but we have to express z by x, right? So from this relationship, we know that x minus mu is equal to az, okay? Which implies that z is equal to the inverse of A times minus mu. Yeah. Okay? This is the inverse. Okay? And so that's Z transpose, and Z becomes to A inverse mu. This one transpose A inverse and x minus mu. Okay, so this is becomes to x minus mu transpose and A inverse transpose A inverse here. Okay, and x minus mu. All right, so we have this. Now, the transpose of the inverse of A is equal to, okay, so it's equal to the A transpose inverse of A inverse, okay, and x minus mu. Right. All right, so these two, so we can exchange the inverse and the transpose, right? From linear algebra. All right, and so this is x minus mu transpose. All right, and this is A transpose inverse of x minus mu. Okay. Now, as we know that the covariance matrix, it's A transpose. Okay, the covariance is, and the determinant. Okay, so we see that the covariance matrix of X is A transpose. This is the first, and the determinant of lambda X is the determinant of A transpose. And so this is determinant of A and determinant of A transpose, okay, by the product formula of determinants. And this is determinant of A, but the determinant of A transpose is the same as the determinant of A, so that this is the square of the determinant of A. Okay, so the square of determinant of A is equal to the determinants of the covariance matrix of X. Okay. All right, so that we have 2 pi to the n square and determinant of lambda x. Okay, this is lambda x. And the exponential function, right? So we just make the substitution, transpose, and the lambda x inverse. Okay, so this is lambda x, and x minus u. And okay. Oh, I forgot. This is. Okay. Okay, so we have done. So basically, we apply theorem 6.7.b, okay, to find a joint PDF of this n jointly normal random variables x1 up to xn. Okay. All right. And apparently, if even if m equal to n, but if A is not non-singular, then, all right, then the covariance matrix lambda is not the non-singular, means that this is singular, okay, and so that we can't have this one because the inverse does not exist at all, okay, does not exist at all. So we have so when m equal to n, we need A to be a non-singular coefficient matrix to guarantee that the n jointly normal random variables are jointly absolute continuous. Okay, jointly absolute continuous. All right, and so there is a question raised up: what happened when m not equal to n? All right. So, or when m equal to n, A is singular. What is the distribution of this jointly normal random variable x1, x2 up to xm? Okay. So we still questions to be answered. Okay. All right. So this joint PDF will be called an n-dimensional or n-variate normal PDF. Okay, with mean mu and positive definite covariance matrix. Lambda x. Okay. All right. Now, so to consider the distribution of m jointly normal random variables, okay, we will compute their joint moment generating function. All right. So now, to compute the joint moment generating function of the m jointly normal random variables x1, x2 up to xm. Okay, so T1, T2 up to T sub m, which is the expectation of exponential function of T1, x1 plus T2, x2 plus plus Tm, xm. Okay. All right, so we'd like to compute this joint moment generating functions. We observe that for fixed, so we first fix the parameters T1, T2 up to Tn. All right, so Tm. So we will fix this m parameters. All right, then we have a random variable. Okay, which is fixed. The parameters are fixed. So this is a linear combination of x sub I with coefficients t sub I. Right? And so t sub I. Okay. And each sub I is a linear combination. Okay. Of z sub j plus a constant. Okay? And so that we exchange the order of summation. So you have Ti and Aij J plus summation of I from 1 to m and the Ti mu I. Okay? Okay, so you can see that this y random variable, as you can see again, is the normal random variable. Okay? Why? Well, because ZJs are independent, all right, normal, standard normal random variables. So that when we multiply with a constant, this constant times ZJ, so the terms here in this sum are independent normal random variables with zero mean, and the variance will be the square of this sum, okay, for each z sub j. Okay, and so by proposition 6.3.2, this sum, right, becomes to a normal random variables with zero mean and the variance, which just the sum of the square of these terms here. Okay, and when we add a constant, so we know y. So y is now we have that this y, okay, x is a sum of n independent normal random variables. Okay? Okay, and for plus a constant. This constant is here, is this sum. Okay? So y is the sum of n independent normal random variables plus a constant. So that y is a normal random variable with mean. All right, so the mean is expectation of y, which is equal to summation. Okay, so this can be written as T transpose mu. Okay, and here the T vector would be T1, T2 up to Tm here. Okay, right, so with mean and variance. Okay, so we compute the variance of y. And the variance. Okay, so which is equal to okay, and from our we know this is Ti and Tk and covariance of Xi, Xk. Okay, it's here. So I think it's okay. If we have to wrap this formula, but if you forgot it, that's fine. We just say the variance is the covariance of the sum and itself, right? But we use different dummy index here, so that right. So by the linearity, okay, here. Okay. All right, and so we know this covariance is the ij entries of the covariance matrix of X sub i's. Okay, so this is actually the quadratic form, right? And so this is T transpose and the lambda T, okay, X where lambda x is the the covariance matrix of x1, x2 up to xm. Okay, so the variance of y is this covariance. This quadratic form. Okay. Now, because y is a normal random variable, so we know that the moment generating function of a normal distribution, okay, is equal to the exponential function of the expectation of y times t plus 1/2 of the variance of y t squared. Okay. Right. So the joint moment generating function, right? Okay, as we know, this is expectation of EY. Okay, because y is defined to be this sum. So y is just the coefficients, the exponents here. All right, and this is actually is the my1. All right, so this can be obtained by taking t equal to 1. Okay, so this is my1 here, and so that we have the exponential function of the, because t is 1, right? So this is EY plus 1/2 of the variance of y. Okay, so y, and so we will expectation is this one. So this is exponential function of t transpose of mu plus 1/2 of this quadratic form. So it's t transpose lambda x and t. Okay. Here, and we can write denote by using vector form. This can be written as mx and t here. Okay. So that t is the exponential function of t transpose mu plus 1/2 t transpose lambda x t. Okay, so the moment generating function, you can see that it's an exponential function, and this is true for all t in Rm. Okay, so you can see that the joint moment generating function of x1 up to xm, right, is defined on the whole m-dimensional Euclidean space. Okay. Okay, so you can see this joint moment generating function is very nice. Okay, because it's an exponential function. Okay. Okay, and note that we know that the covariance matrix A transpose. Okay, it's A transpose that. Okay, so once we have the jointly moment generating function, and this joint moment generating function can determine. Okay, so it determines a unique joint CDF of x1, x2 up to xm. Okay, so from the one-to-one correspondence. Okay, especially we stated in proposition. I think it's proposition 7.7 and I. Okay, 7.7i there. Okay, so we should have that. Okay, so we have shown the joint moment genuine function of M jointly normal random variable has this form. Okay, has this form. Okay, so we will use this joint moment genuine function of M jointly normal random variables to study the distribution, okay, of M jointly normal random variable. All right. So first of all, we first assume that the M times M covariance matrix lambda x, right, of x of i's is non-singular. i.e. Positive, definite. Okay. And from linear algebra, okay, from linear algebra, lambda x, which we know is A transpose, is non-singular. Right. So this is M times M, this is M times N, and transpose is N times M. Right. It's non-singular if and only if the rank of A is equal to what? To M. Okay, so rank of A is M times N. So this is the only condition we have, right? So that for an M times M matrix has rank M, which means that M must be less than or equal to N, all right? So M is at most equal to N, but can be less than N, okay? And so this is the case that that the covariance matrix is non-singular. Okay, so we know that. All right. So in this case, now by the real by the real spectra theorem, right, we have that the lambda x can be decomposed to u, d u transpose, okay? And this is u, and square root of d, and the u transpose. And you know, because the diagonal matrix has diagonal entries, they are eigenvalues, but since the coordinate matrix is positive definite, so every diagonal entry is positive, we can take the square root, okay? All right, so take the square roots, all right, and so this is u, square root of d, and u, square root of d of transpose here. With u and m times m real orthogonal matrix, okay, and d and m times m real diagonal matrix, okay, having positive diagonal entries. Okay, like entries, right? Now we let A to be u square root of d. Then A is an m times m real non-singular matrix, and lambda x becomes to A transpose. Okay. All right. Now we let z vector to be A inverse of x minus mu. Okay. Which says that x becomes to A z plus mu. Okay. Okay. Oh, our purpose is to. Okay. I think I have to write the purpose here. Maybe I write here. All right. So we next. All right. All right. So okay. All right. Up to this point, we know. If xm, x1 up to xm are m jointly normal random variables, okay? Then we know that their joint moment generating function is this form. And we want to show that this, next show that if m random variables, x1, x2, up to xm, have a joint moment generating function all right, m, x1, x2 up to xm, t1, t2 up to tm is equal to this an exponential function of this form. Okay, if this has, so if this m random variable have a joint moment generating function of this form, then x1, x2 up to xm are jointly normal, right? Jointly normal, which means that x vector should be an affine transformation of z vector, and the z vector consists of random variables which has normal distribution, has the z vector has components which are independent standard normal random variables. Okay. All right. So what we want to do is to show this fact. Okay. Okay. So our job is to show that if we have m random variables, and whose joint moment generating function take this form, where mu is the mean vector of this m random variables, and the lambda x is the covariance matrix of this m random variables. All right, then we will show that this m random variable are joint normal. Means that this m random variable can be obtained by affine transformation of a set of independent standard normal random variables. Okay. Okay, and so we this is what we want to do. We will split the discussion into two cases. The first case is that we assume the covariance matrix is non-singular, all right, which means that it is positive definite. So we can apply the real spectral theorem, okay, and then we can decompose the covariance matrix lambda to be the product of A and A transpose. So actually we construct a matrix A, okay, construct a matrix A here, okay, which is a real non-singular matrix. All right, and so we let Z to be, all right, this linear transformation of the difference of this random vector, okay, by using the inverse of A, okay. In that case, then X becomes to be affine transformation of random vector Z. Okay, and so we will show that random vector Z consists of m independent standard normal random variables. Okay, and this can be seen by computing the moment generating function of Z. Now, the moment generating function, the joint. So the joint moment generating function of z, vector z, all right, it's z1, z2 up to zm. Okay. So M dt transpose, the expectation of exponential function of t transpose z. Okay, so this is the, note that. Okay, all right, so this is what we want. Okay, and the expectation of exponential function of the t transpose. And z is here, so by the substitution, A inverse of x minus mu. Okay? All right, and so this comes to the product term t, all right, and times e exponential of t mu. Okay, so this is a constant. Okay, this is a constant. So by linearity of the expectation, this has become to E t times E dt A inverse mu here. Okay, and now we look at and we compute x, okay, by the joint moment generating function of xi's. Okay, and this is expectation. So we have A inverse transpose T transpose X. Okay. So we rewrite because you hear T transpose A inverse. This is T transpose A inverse transpose and transpose. Okay, so we have transpose. Now this is A inverse transpose T transpose. Okay. Okay, and so now this is exponential function of so that this is the A transpose T, okay, and the mu. So this is the transpose mu. Okay, plus 1/2 A transpose T transpose and the lambda of X. Okay, and A inverse transpose T. Okay. All right. So this is actually, so this product is equal to this T. Okay, the same, this T here. Okay. Right. So this is just like a T itself. Okay, and the T transpose times the mean vector of X. Okay, and plus 1/2 of the transpose of this vector times the conventional matrix of X times this vector here. Okay, so this expectation is equal to this one, here. Oh, well, forgot this is minus. Okay, because we have minus term here. Minus. I'm sorry. Okay, and so now. So now the joint moment generating function of random vector z becomes to this expression. So it's this expression of and here we have transpose T, and the A inverse of mu, okay, times exponential function here of 1/2, okay, and T is A inverse, and the lambda X, and A inverse transpose and T, okay, times exponential minus T, this vector, A inverse and mu. Okay, here. All right, and so you can see that this is the inverse of this one. All right, so the product of these two is equal to 1. All right, so this is become 2 here. All right, and A inverse, but the lambda, the conventional matrix, as we see, is A. So this is A transpose. And A inverse transpose is equal to A transpose minus, okay, and T here. All right, since A inverse transpose is equal to A transpose inverse, okay. All right, so that you can see this is identity. So we have T. Okay. Okay, and which is the joint moment generating function of M independent standard normal random variables. Okay, so we know that. So that's Z1, Z2 up to Z sub M are independent standard normal random variables. And then X, which is A, Z plus mu. Then with X equal to A, Z plus mu. X1, X2 up to Xm are jointly normal by definition. Okay, so we have shown that for the case that the covariance matrix is non-singular, then we can find M independent standard normal random variable such that X is the affine transform of Z. Okay, and here mu is just the mean vector of X, and A is obtained by the spectral decomposition here. Okay, so we define A to be this one. Okay, and the Z, Z is constructed as an affine. So this is the linear transformation of this random vector. Okay, by construction. Okay, so we have done for this case. All right. So the next, we next assume that the M times M covariance matrix lambda X of X1, X2 up to Xm is singular and of rank n such that n is from the 0 to m minus 1. Okay, so now we consider the case that the covariance matrix lambda X is singular and has rank n is between 0 and m minus 1. So now we apply proposition 7.8.a. Okay, R, which m minus n out of m random variables x1, okay, without loss of generality, says xn plus 1, xn plus 2 up to xm. Okay. All right, so we have this R. So the R and affine transform of the rest and random variables x1, x2 up to xn with probability 1. Okay. And whose covariance matrix, we say number 1 is non-singular. Okay, in particular, we have x2 minus mu2 is equal to b, x1 minus mu1 with probability 1, where x1 is the first n random variables mu1 is the mean of the first n random variables. X2 consists of the last R random variables. Okay, so we know we have that. Okay. For some R times n real matrix B. Okay, and then x minus mu is equal to with probability 1. Okay, so when we subtract the random vector corresponding to the m random variables, so this is the m times n, m times 1, right? Okay. And this is n times 1, n times 1. And the matrix is m times n. Okay. All right. So, and also okay. Now, since x1 is equal to identity and the zero matrix times the x. Okay. Yeah. So the random vector x1 consists of the first n random variables, x1 up to xm. Okay. Okay, so you can see that the x1 random vector is this matrix times this random vector. Right, so we can use that. Okay, we can use that to find the moment generating function of x1. Okay. Okay, so the joint moment generating function of x, random vector x1 is okay here, right? So this is the the x1 consists of the first n random variables, and we know the n here is the rank of the covariance matrix of the original random vector capital X. So that's T1, okay, and T1 up to Tn. So it has little n parameters. Exponential function of T1t and x1. And so exponential function of T1t and x1 would be identity 0 x here. Okay, and so now to use the joint moment generating function of the original random vector capital X, so we know that this is the T1 transpose, and so we can reverse order of the matrix. So this is identity n order r equal to n here. Okay, so that is this one. Okay, so the product here becomes the transpose of this product. Okay, and so that this is the exponential function of this product mu, right? Mu function, mean function of random vector capital X plus 1/2 lambda x and transpose lambda x this one. Okay. All right. and so that so when we do the multiplication, this is actually T1, and this is 0 vector, so transpose mu here. Okay, plus 1/2, and this one is T1, 0 vector, transpose lambda x, and T1, 0. Okay, here. Okay, and as we know, the mu, we know mu is actually mu1 and mu2. And we know lambda can be lambda 1, okay, and other things. Okay, so lambda 1 is x. So this is the covariance matrix of x1. Okay, so you can see that lambda 1 consists of covariance of xi, xj, such that I get j in between 1 and n. Okay, all right. So this is just this part. And when we multiply with this vector, okay, we find that, so this is exponential function of T1 transpose of mu1 plus 1/2 T1 transpose and the lambda 1 and T1. Yeah. Okay, so so you see that x1 there. So, and we have shown that the joint moment general function of random vector x1 has this form, and we see mu1 is the mean, all right, of x1. And lambda 1 is the covariance matrix of x1. Okay, so we know that. So this implies that on x1, x2 up to xn, okay, are jointly normal. Okay. They are jointly normal here. Okay. As in the previous discussion, because all right, so because that we have discussed the case that when the covariance matrix of random variable is non-singular, and the moment general function take the exponential of this type, then the random variable should be joint normal. Okay, so we have see that. All right, so we have, this is our joint normal, okay, in the And x1 is equal to A times Z, okay, plus mu1. Okay. Okay, for some non-singular n times n matrix A. Okay, as we have shown here. Okay, we have shown here. All right. So this is from. So that we have that because number one is non-singular. This is guaranteed from proposition 7.8.8 here. Okay. So that's why, because number one is non-singular, and so we have, as we have discussed in the previous discussion, that the first n random variables are jointly normal, okay, and so x1 is and the n components z1, z2 up to zn in the random vector are independent standard normal random variables. Okay, so first of all we have this one. Okay, and so finally, that here, right? Now, so that and finally, x here minus mu is equal to this matrix and x1 minus mu1. But x1 minus mu1 is equal to a z here. So this is equal to A and BA Z. So that X is equal to a matrix A, BA, Z plus mu. Okay. This which shows that x1, x2 up to xm are jointly normal. Right. So finally, because the X is a matrix, so it's an affine transformation of n independent standard normal random variables. Okay. Okay, and so we summarize that. So now we summarize the above discussion. In the following proposition. Okay, so we'll say that proposition 7.8.c. If m random variables x1, x2, up to xm have a joint moment generating function, which is here. Where T is the this parameter vector, and mu and the lambda are the mean vector, and the covariance matrix of the random vector respectively, right? So if we have this situation, then x1, x2 up to xm are jointly normal, and the random vector x can be written as az plus mu. Maybe I will write it as cz plus mu with probability 1 for an m times n real matrix C of rank n, okay, of rank n. You can see this is C, right? And C has rank n because A is, we know A is invertible. So this is, A is n times n matrix, is invertible. So this matrix has rank n. Okay, and this rank n, which, okay, is equal to the rank of the covariance matrix lambda, okay, and a random vector z, where the n random variables z1, z2 up to zn are independent standard normal random variables. Okay? All right. So in this proposition, we summarized the two cases we discussed in above. Okay? Joined together. Okay? So we have answered our question that whenever if we know m random vectors, random variables have a joint moment generating function with this form. In here, mu is the mean vector and lambda is the covariance matrix of these m random variables. Then these m random variables are joint normal, which means that we can this m random variables is an affine transform of n independent standard normal random variables z sub j's. And the n little n here is the rank of C, and this rank of the coefficient matrix C has the same rank as the covariance matrix lambda. Okay, so basically we have answered the questions we have. Okay. So now we have a couple of propositions as the consequences of the above discussion. So proposition 7.8.d, so let x1, x2 up to x m be jointly normal random variables with a covariance matrix, okay, lambda. Okay, right, so we consider m jointly normal random variables and with this and with covariance matrix. Then x1, x2 up to xm are independent. Okay, so they are independent if and only if, all right, lambda is diagonal. The proof for the 4 pi is very simple. The reason is that things, because there are things xi and xj are independent. okay, are independent. The covariance of xi and xj, as we know, which is the xi minus mu I times xj minus mu j, expectation. Okay, and because that xi and xj are independent, so this random variable is independent of that random variable. So the expectation is equal to times expectation. But this is 0. 0 times 0. So this is 0. Okay. So you can see that the off-diagonal entries are always 0. And then lambda is diagonal. Okay. Because the off-diagonal entries is when I not equal to j, the covariance is 0. Okay. Okay. So the four directions is simple. Now, for the brickwork direction, we need the joint normality. Okay. For the four direction, we don't need to know that x1, xm are jointly normal, right? We just need that this m random variables are independent. Okay, it's the sixth independent. So, okay. All right. So since x1, x2 up to xm are jointly normal. Okay, so they are joint moment generating function is here, x exponential function mu plus t. Okay, and so that we have exponential function summation of pi mu I plus 1/2 of exponent of that I from 1 to m and lambda I ti square. Okay, since lambda equal to lambda 1 implies that because lambda is diagonal, so we can write it in. And so T1, T2, Tm okay, so this quadratic form becomes to be lambda 1 T1 square plus lambda 2 T2 square plus plus lambda m Tm square. Okay, so we have that. And okay, and we know we can split this into, so this is become to the exponential of T1 mu1 plus 1/2 lambda 1 T. Okay. Oh, by the way, because diagonal, so this is the variance. Okay. So the diagonal entries are just variances. Okay, so that's 1 square So here we have sigma I square. Okay, and so here we have sigma square T1 square E T2 mu 2 plus 1/2 sigma square T2 square exponential Tn Tm mu m plus 1/2 sigma m square Tm square. Okay, and you can see this is just the moment generating function of x1, because we have shown that if m random variables are jointly normal, then each of them has normal random variable. Okay, so this is m1 and t2. Okay, so the joint moment generating function of x1 up to xm is the product of the moment generating function of each xi's. All right, and so that. Okay, so we have that. Okay, now by proposition 7.7.I, item 3, the x1, x2 up to xm are independent random variables. Okay, so we have shown this result. Okay, so that this is from the proposition we have in the moment generating function section. Okay, so we prove this one. And the other proposition, 7.8.E. So we let x1, x2 up to xm, y1, y2 up to yn be jointly normal random variables with a covariance matrix lambda. Okay, right. So suppose we have m plus n jointly normal random variables, and their covariance matrix is lambda. Yeah. Then the X collection and the Y collection are two independent collections of random variables. If and only if the covariance matrix lambda is block diagonal, means that lambda can be written as where lambda x and lambda y are covariance matrices of the X collection and the Y collection respectively. Okay. So this is M plus N times M plus N. This is M times M. This is N times N. So it's block diagonal. Okay, so you can see that the proof, the forward direction is simple. So since these two collections are independent, the xi and yj are independent. For all I from 1 to m, and for all j from 1 to n, so that the covariance of xi and yj is 0, okay, as we shown before, right? And as we know, the opdag, the entries is in here, in this block and this block, text of the form like this one. So they are all zeros, okay? So that's lambda is equal to is block diagonal. Okay, so it's simple. So the forward direction just need that these two collections are independent collections. We don't need the condition that these m plus n random variables are jointly normal. We don't need that. But for the backward direction, we need that, okay? So for the backward direction, yeah. So now, so since x1 up to xm, y1 up to yn are jointly normal. Okay, jointly normal. So their moment generating function is, all right, so we will compute the moment generating function of this m plus n random variables. Okay, so all right, this has become to be the exponential function of T and X transpose and the mu and the eta. Right? And mu, so T, T1, T2 up to Tm, and X, S1, X2 up to Xn. Mu is the mean function. Okay, so that is the expectation of x1, x2 up to expectation of xm. Eta is the mean vector of y. Yeah. And lambda we know is okay. So so we compute T X transpose, and this is lambda X. Okay, all right, and so this is T transpose X transpose, and here is lambda X T, lambda Y S. Okay, so this is T transpose lambda X T plus X transpose lambda Y and S here. Okay, so this quadratic form has two terms. Okay, and similarly for here, T transpose so this is T transpose mu plus S transpose eta. Yeah. Okay, so we have exponential. So we have two terms, T mu plus X transpose eta plus 1/2 T transpose lambda T X plus 1/2 transpose lambda Y. Okay. Okay, and so you can split to times exponential. And this is the moment generating function of the X collection. And the second factor is the moment generating function of the Y collection. Okay, so the moment generating function of m plus n random variable becomes the product of the moment generating function of the first m random variable times the moment generating function of the rest n random variable here. All right, and so by proposition 7.7.I-4, okay, these two collections are independent collections. Okay, so this is the end of the proof. Okay, so we will use the previous result to prove a proposition which is important in statistics, right? So we consider, so we let x1, x2 up to xn be a sequence of independent and identically distributed identically distributed normal random variables with mean mu and variance sigma square. So these n random variables are independent normal random variables with the same mean and the same variance. Okay. And also we let x bar to be the sample mean. We call the sample mean of x sub I is, okay, right? So x bar is just a linear combination of these n random variables. Okay, so x bar is a random variable too. And it can be shown that it can be seen. Okay, so it's easy to see that the expectation of the sample mean is the same as the mean of each random variable x sub I. But the variance of the sample mean x is the variance of the original random variable divided by n. So you see that as n goes up, the variance of the sample average decrease. Okay, all right, and going to 0 as n going to infinity. Now we consider. So now xi minus the sample mean is called the ice deviation. Called the ice deviation. Okay, and which is the difference between the ice data x sub I and the sample mean x bar. Okay. Now, okay, so now x bar is minus mu. Okay, so sigma plus okay, and plus mu. Okay. Okay, so the sample mean can be expressed as linear combination of this is what? This is the standard normal random variable because each x of I, right? So that so we know this is showing that this implies that zi defined to be xi minus mu divided by sigma is standard normal random variable, okay? Because the mean of zi is 0 and the variance of zi is 1, okay? And so we know that, okay? So this is zi is standard normal random variables. And so so that z1, z2 up to zn are independent standard normal random variables. Okay, and so we can express x bar as a linear combination of these sub i's plus a constant. Okay, so this is okay. So you can see that what we have, and the deviation x1 minus x bar. So this is the first deviation. And the first deviation, well, so we can see here. So that x1 sigma and sigma n minus 1 divided by n minus sigma n sigma x2 minus mu minus minus sigma n xn minus mu sigma. Okay, and minus mu. Let me see. Minus mu and also minus n divided by mu. Okay. Okay. And go down up to the nth deviation. Okay. So the nth deviation would be minus and finally, which is sigma minus 1 and sigma xn minus mu divided by n. Okay. Okay, and we know that this is Z1, this is Z2. This is Zn. So from that, which says that x1, x bar, and the first deviation, the second deviation up to the nth deviation. Okay, so we have n plus 1 unknown variables jointly normal random variables. Okay, so they are jointly normal random variables, and we look at the covariance of the sum of mean and the ith deviation. And so since the covariance of x bar and the ith deviation, okay, so we have, so this is covariance of x bar, xi, minus covariance of x bar, x bar. Yeah. And this is covariance of xk and xi. And this is, as we know, this is the variance of x bar, and which is equal to this quantity. Okay, so now and by proposition 7.4.2, this is equal to M1 covariance of xk and xi. And, okay, so by proposition 7.4.2. Okay. All right. But because that xi's are independent, so if k not equal to I, the covariance is 0. So that this is the covariance of xi. And this is So it's 0. Wow. Okay, so the sample mean, the covariance between sample mean and the ice deviation is 0. All right, so this implies that so the covariance matrix of sample mean and the I deviations, okay, is block diagonal. Okay, it's block diagonal. Which i.e. lambda is equal to sigma square divided by n 0, 0, and the lambda 1 here. Okay, and this one is the variance of x bar. Okay, so this is equal to the variance of x bar here, and that they are all zeros in here. So this is the block diagonal. Okay, so the covariance matrix is block diagonal. All right, and now by proposition 7.8.E, okay, so this proposition here, okay, because the covariance matrix is block diagonal, so that the x bar is independent of the collection, the deviations. Okay, so x bar is statistically independent of collections. All right, now define. So the s square I from 1 to n of the. So you can see that this is a function of the n deviations, okay? A function of n deviations. It's called the sample variance of x sub i's. Okay, this is called the sample variance of x sub i's. And it can be seen that the expectation of the sample variance is equal to the variance of the size. Okay, so this is a very good or so-called unbiased estimator for the variance of a sigma xi. Okay. So that's why it's a very good estimator. Just like a sample mean, because the expectation of the sample mean is mu. Okay, so we can use the sample mean as an estimator of the mean, right? Mu, yeah. Okay. So in statistics, we usually want to find estimators to estimate the mean and the variance, right? Because usually we don't know these two parameters, okay? We don't know these two parameters. So we can use the observed data to estimate the mean and the variance. And the sample mean is a very good estimator for the mean because its expectation is just the mean here. Okay, and the sample variance, all right, sample variance. So you can see that is the data minus the sample mean, all right. And so this is called the deviation. We take the square, okay, and divide the sum of the square of the deviation and divide by n minus 1. And it is not divided by n, it's divided by n minus 1 because that only divided by n minus 1, the expectation of the sample variance is the variance of the random variables. Okay, so we can see that. And this actually you know the deviation of this result in section 7.4 in the textbook. So I think you can refer to the result. Okay, and so that the important thing is that we have two estimators. This, so x bar, the sample mean, and we know that's distribution. Why? Because this is a linear combination of xi's. So we know x bar, the sample mean, is normal distribution, has mean, which is mu, and the variance, this one. Okay, so we know the distribution of this bar. But what is the distribution? So what is the distribution of the distribution of the sample variance? And also we may want to know what is the relationship between the sample mean and the sample variance. Okay. So we have quite a few questions answered. Now we look at this one. We know that. So know that s squared is a function of the deviations of x1 minus r. Okay? So that as a function of these collections, S bar is statistically independent of X bar. Okay? Because we know X bar is independent of these collections. So X bar is independent of any functions of these n deviations. Okay? So at this moment, we know that the sample variance is independent of the sample mean. Okay. All right. Now to find the distribution of so the relationship here, we know that the x and the x squared and s bar, they are independent. They are independent, statistically independent of each other. Okay. Right. So, and we know the distribution of this bar. So the important thing is to know the distribution of s squared. But before to know the x squared, we are actually now the square, okay, the square is of a standard normal random variable z, okay, is a gamma random variable with parameter alpha, which is 1/2, and lambda is 1/2 too. Okay, so we know that from, say, chapter 5, right? So you know, chapter 5, we know this factor. And its moment generating function. And okay, and the moment, so the moment generating function of this square, okay, it's here, mg square t is 1/2, and 1/2 minus t of 1/2. So this is 1 divided by 1 minus 2t, 1/2. Okay. All right, so that this is the I. And the sum z1 square plus z2 square plus zn square of the squares zi of n independent standard normal random variables z1, z2 up to zn. Okay, is a gamma this random variable, okay, with parameters alpha equal to n divided by 2, and lambda is 1/2, right? And which is called okay, so which is said to have a chi-square distribution, a chi-squared distribution with n degree of freedom, and its moment is moment generating function x here of t okay, so that is okay. Okay, and so now we can state proposition 7.A, point F, to say that n minus 1. So a scaled sample variance, right? So this is sample variance, but multiplied with this constant is chi-squared random variable with n minus 1 degree of freedom. Okay. Okay, so after we scale the sample variance with this particular constant, this random variable becomes to a chi-squared random variable. Okay. Okay, so now we give a proof. We first know that. Okay, we multiply with the sample variance by n minus 1. We know that this is the sum of the square of the deviations. Okay, so we have that. And actually, we can do that. We can subtract one thing, but add one thing, right? So we have square. Okay, and so this becomes to summation of I equal to 1 and n, and xi minus mu square minus 2 summation I from 1 to n, and xi minus mu x bar minus mu plus summation I from 1 to n x bar minus mu square. Okay. All right. So xi minus mu square. Yeah. Now this is something independent of the index. All right. And so we have this one. Okay. And this is independent of the I, so we have n copy of the square. Yeah. And we look at this one. You can see this is the summation of x of I minus n mu. Okay. All right. So we have that. And this is equal to n times n s bar, okay, minus n mu here, right? So that this is equal to n times x bar minus mu. All right, so you can see this becomes to n of the square of the difference. All right, so that by calculation, minus n x bar minus mu square. Okay. All right. So that this scale, the sample variance becomes to the sum of the square of the difference minus n times the square of the difference here. Okay. And now we divide both of them by the sigma square. Okay, so we move this to the right hand side. So now we have n minus 1 s square plus n of x bar mu square equal to summation n and xi minus mu square. Now, if we divide the sigma square on both sides, so we divide them square, okay, and divide them as a square. So now we have a minus 1 square plus here we have mu and sigma divided by square root of n square. So you can see that it's a kind of normalization because S bar has mean mu and the variance, okay, and the variance of sigma square divided by n, and so this is the standard deviation of the S bar. Okay, all right, and so after this normalization, this is actually a standard normal random variable. Okay, so this term is a standard random variable, and here square, and again you can see that this is also a standard random normal random variable. Okay, so this standard normal random variable, and also this one a standard normal random variables. Okay, now okay, so that because they are equal, so the sum, this sum has the same moment generating function as this, okay, the moment generating function of this sum. But from our previous discussion, okay, so you can see that this is the g sub i here. You can think about this is g sub i, and so the moment generating function is actually the moment generating function of the chi-square distribution with n degrees of freedom. Okay. Okay. So that so the moment generating function. Okay. So the expectation of okay, sigma square plus z t is expectation of E summation I from 1 to n z I square t. Okay, and so we let this to be zi, this to be z. Okay, with z equal to and being standard normal random variables. All right, and we know this has a chi-square distribution. Okay. Oh, square. I'm sorry. Here. Yeah, this square. All right. So we have 1, 2. All right, and here, because this term, this is a function of the deviations. This is a function of S bar. So these two terms, these two random variables are statistically independent. Right? So times expectation. Oh. Right. And things are independent. Okay, so they are independent. So you have that. All right. But z square, so we know that this has chi-square chi-square distribution with 1 degree of freedom. Okay. All right, and so the moment generating function of this one is equal to divided by here. This is half. Okay, so that this becomes 2 and minus 1 divided by 2. Okay, so which implies that has chi-square distribution with degree with n minus 1 degrees of freedom as we desired. Okay, as we desired. So we have proved this proposition. Okay, so the scaled sample variance is chi-squared random variable with n minus 1 degrees. Degrees of freedom. Okay, so we have shown that. Okay, so we conclude our discussion in the following proposition. One. So if x1, x2 up to xn are independent and identically distributed, normal random variables with mean mu and the variance sigma square Then the sample mean x bar and the sample variance are independent. Okay. Furthermore, x bar is a normal random variable with mean mu and variance sigma squared divided by n, and n minus 1 divided by square root by sigma square times the sample variance is chi-square random variable with n minus 1 degrees of freedom. Okay. Right. So this is the end of our discussion about properties of jointly normal random variables. Okay. Right. So I have completed the discussion of chapter 7, and then I will continue to study chapter 8 the next week. Okay, so I stop here.